One of the really important concepts in trying to understand how the valence electrons in a particular element are going to behave is to understand how tightly they are held to the nucleus. So how strongly are these valence electrons attracted to a particular nucleus? So if we think about lithium, which has an atomic number of 3, so it has a positive 3 plus charge in the nucleus, and it has an electron configuration that has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. Or if we think about beryllium, which has a 4 plus charge on the nucleus with an atomic number of 4, also having 2 electrons in a 1s orbital, but now having 2 electrons in the 2s orbital, we can start to think a little bit about how strongly these valence electrons are attracted to the positive charge in the nucleus. So to do that, we're going to look at these electron density plots. So what we're looking at here is little dots. So if I measured where the electron was, so if the electron was described by a 1s orbital, if I measure where the electron is a whole bunch of times, it's going to be scattered about the nucleus. The nucleus is right in the middle of this electron density plot. And the electrons are going to be scattered about that nucleus. And I'm most often going to measure the electron as being pretty close into the nucleus, but every once in a while I see it out here a little bit further out. So in that 1s electron density, the electrons are staying very close to the nucleus. In the 2s electron density, there's a probability that they're pretty close to the nucleus, but then there's a node where there's no probability of finding the electron, and then the majority of the time I'm measuring the electron out here further away from the nucleus. So remember that we said that the n quantum numbers, so n equals 1 or n equals 2, tells us not only about the energy of those electrons that are described by those orbitals, but also tells us about the size of those orbitals. In other words, how far away from the nucleus is the electron most likely to be found. So I can also graph this in another way. I can graph it this way. And what I'm thinking about here for this radial probability graph is that if I walk out from the nucleus in any direction, in this 1s orbital, I'm initially not going to have a probability of having the electron at the nucleus because it can't be inside the nucleus. But as I walk away from the nucleus, I have a very sharp rise in the probability. There's a high density right near the nucleus. And then as I keep walking out away from the nucleus, that probability drops off to close to 0. However, for the 2s orbital, so we're looking at the green curve here, I have a little bit of a probability close in. So that's that yellow density in the middle there. Then it drops to 0. That's my node. And then as I keep walking out, I have the highest probability further away from the nucleus. So what that means is that these core electrons, the 2 electrons that are in the 1s orbital configuration, those core electrons are in closer to the nucleus than these valence electrons. So there's 2 things that are important. When we're talking about plus minus attraction, the distance from the positive charge, so the distance of the electron from the positive charge in the nucleus, is going to make a difference. And the further away it gets, the less the attraction. The other important thing is that not only distance, but also the positive charge that the electron is being attracted to makes a difference. So the charge matters, and so higher positive charges will attract the electron more strongly. So that means because beryllium has a 4 plus charge and lithium has a 3 plus charge, all of these electrons should be more strongly attracted to the beryllium than these electrons are attracted to the lithium nucleus. So we would expect that the electrons in beryllium would be more strongly attracted to the positive charge in the nucleus and therefore would be closer in to the nucleus because they're pulled in more tightly, and so they're closer into the nucleus than compared to the lithium, which are only pulled in by a +3 charge. So that's the first thing to think about, is that the higher the charge, the more strongly the electrons are attracted, so the closer into the nucleus they're going to be. Now, the other thing that affects this, though, is that the electrons that are in the core, so these 2 electrons that are in the 1s configuration orbital, these guys are in closer to the nucleus. And so they stay in closer to the nucleus. And these are relatively to scale, so these 2s electrons are out here. So if we look at this distribution, the 2s electrons are mostly out here away from the 1s electrons. So we can think about, for instance, if we have a sun on a very hot sunny day, and we're down here on the earth someplace. So we're down here enjoying the sun, right? And enjoying all of those beautiful sun rays. But then a cloud comes across the sun. And when that happens, we don't see as much sun, and we don't feel the heat of the sun, and it cools off. So when we have something between us and the sun, we don't feel the attraction of the sun as strongly. That analogy can be used to think about how these core electrons are going to affect the valence electrons. So if I have 2 electrons in here close to the nucleus, they're going to act as a cloud on the nucleus. So the analogy here is that the sun is the nucleus and the core electrons are the cloud, and I am the valence electrons. So if I have core electrons that are covering, shadowing the sun, then I'm not going to feel as strong as an attraction. So the core electrons, what we imagine is that these core electrons are going to shield the valence electrons from the nucleus. So in summary, when we're thinking about how strongly a valence electron is attracted to the nucleus, we have to consider the charge on the nucleus, and the higher the charge, the stronger the attraction. We have to consider how large the orbital is that those valence electrons are in. So the higher n levels are larger orbitals, 1s, 2s, 3s. And the further away the electron is, so the larger the orbital, the further away that electron is most likely to be, the lower the attraction to the nucleus. And then finally, the more core electrons we have that are shielding the nucleus, the more shielding we get, and that lowers the attraction of the valence electrons to the nucleus. So all of these things lead to a concept that we think about in terms of the effective nuclear charge. We have the symbol Z effective. So Z sub EFF for Z effective. This concept is the idea that the valence electrons, the ones that are out further away from the nucleus, that are further out from the core electrons, those valence electrons they're going to act as though they don't feel the full charge of the nucleus because they're further out, so they have a lower attraction. And there's core electrons that are shielding, and that also lowers the attraction. So the total nuclear charge might be quite high, but these two factors, which have to do with how the electrons are interacting with each other, are going to lower the attraction of the electrons for the nucleus and make it act as though they have a nuclear charge that is less than the actual atomic number or the actual nuclear charge. So if we think about these three factors and we compare atoms that are in a particular row on the periodic table, so a particular period. So let's look at these row 2 atoms. As we go across the row, the atomic number increases, so we're getting a higher and higher charge. However, each one, as we go across, has the same number of core electrons, and their valence electrons are in the same end shell. So the relative size of the orbitals that are containing the valence electrons is about the same, and they have the same number of core electrons. So as we go across the row, these two second factors are approximately the same going across the row, and what matters is that we have a larger nuclear charge as we go across the row. And so the Z effective for the valence electrons as I go across a row, what's going to happen going across this way is that Z effective for the valence electrons is going to increase because I don't have to worry much about these last two things because they're relatively the same across the row, and the only factor that really matters is the actual charge on the nucleus. So Z effective is going to increase as I go across a row. Now, if we think about what happens as we go down a column, so if we go down a column, clearly the total charge on the nucleus is increasing. We're going from lithium with 3, sodium with 11, potassium with 19, rubidium with 37, cesium with 55, to francium with 87. So clearly the charge on the nucleus is increasing dramatically as I go down the row. So you would think that that higher nuclear charge should pull all of those electrons tighter, or these electrons should be attracted more strongly to the nucleus because of this larger nuclear charge. However, as I go down the column, so I go down a column here, the valence electrons are in larger and larger end shells. So lithium is in n equals 2, their valence electrons are in n equals 2. Sodium, the valence electrons are in n equals 3. Potassium, n equals 4, rubidium, n equals 5, cesium, n equals 6, francium, n equals 7. And so the distance away from the nucleus gets larger and larger and larger, and that decreases the attraction of those valence electrons for the nuclear charge. In addition, each of these has more and more core electrons. So initially, the lithium only has the 2 electrons that are in the 1s orbital from that has the same configuration as helium, so those 2 helium core electrons. And then sodium has 10 core electrons, potassium has 18 core electrons, etc., etc. And so because the number of core electrons is increasing and the valence electrons are in higher and higher orbitals, what we find is that overall, these two factors outweigh the increase in the positive charge. And so as we go down a column, Z effective is going to decrease for the valence electrons as we go down a column.